So this is example number 22.4. And this is the example of a proton in a uniform electric field. Now let's try to read the problem very carefully. So we know that the first thing is to remember that a proton has a positive charge. And then it says that we're going to take a proton and release from rest at point A. So this is point A right here. So what does that tell you about the velocity at point A? Zero. It's zero because it starts from rest. Now this is placed in an electric field, in a uniform electric field that has a magnitude of 8.0 times 10 to the power 4 volt per meter. Then it says that the proton is going to undergo a displacement of magnitude that is given by this. Find the speed of the proton after completing the displacement. Now, if I were to solve this problem, again, each time you have a problem like this, you want to think about this in terms of the physics of the problem, right? So, just looking at this problem here, so we have an electric field. This is my electric field. E. If I take this electric field and I multiply that by the charge on the proton, what does that quantity give me? Electric field multiplied by charge gives me what? It's force, right? So that's a force. Now take this force and multiply this by the distance that the proton is going to travel as it goes from point A to point B. What is force times distance? It's work, which is energy, right? So we know that all of this is the energy, and this energy is going to cause the proton to pick up speed. So the proton starts from rest, the speed was 0, it's going to pick up speed. When something picks up speed, what does that tell you about the kinetic energy of the system? It's going to increase, right? So you're just going to write this as 1/2 times mass of proton times the speed at point B squared. So that's the equation that we need to solve. So I'm just saying that because in this example, the electric field is constant, it's not changing, it's a uniform electric field. Take electric field multiplied by the charge, it gives you force. Force times distance tells you the total amount of energy that is given to the proton. And since the proton is picking up speed, then that energy gets converted into the kinetic energy. So I can solve this equation because I know that VA is 0. So VA is equal to 0. All right. So if you plug in everything here, which is this final equation here, I think you're going to get this equation. So this equation comes from, if you look at this equation here, it's basically the same thing that we're doing. So the equation that I wrote before was saying that 1/2 m B at point B squared minus B at point A squared now, because this is 0, if you solve this equation, you get B at point B which is basically the same equation here, where you just put Q is equal to E because the charge of the proton is the same as the charge of the electron. So this is the same problem here. So we're just saying that the potential energy gets converted into kinetic energy, but you can write that down in this simple form. Now, if you go ahead and substitute everything here, you should end up with this equation. Now let me take a moment here. So let me open my, so I want to take a moment here just to explain. So I want to show you two examples here. So we're going to compare two things. So we have gravity, and then you have electric force. So let's take a small ball. And release that from rest, right? And here, the force that is pushing this ball is the force of gravity. So we're going to release this ball from rest. So let's say that this is floor level. And then the same thing is here. So now you only have a positive charge. Again, you want to release from rest. In the presence of a uniform electric field, I'm just going to say that the uniform electric field has a magnitude of 100. Now, what is the, so here, the velocity at point A here is 0. I want to calculate velocity at point B. Here, the velocity at point A is 0. I want to calculate the velocity at point B. So, in example number 2, in this example, we're going to neglect and I think if you remember from our exam number 1, we said that for most of the calculations that we're going to do, when you calculate the electric force, it's going to be way, way larger than the force of gravity. So if I have an electric field, I don't need to worry about gravity, right? Because gravity is going to be very small. How would you solve the problem this problem right here? So for gravity, you say that, so take mass of ball times gravity times the height should be equal to increase in kinetic energy, 1/2 mass VA squared minus V. Now, I'm sorry, VB squared minus VA squared because we didn't change. So VB squared minus VA squared. Let's see. Now, what is M times G times H? What is M times G? Mass times gravity gives me what? So gravity is acceleration. Mass times gravity gives me force. What is force times height? It's energy, right? So do you see that this is called the gravitational potential energy, UG? So gravitational potential energy is mass times gravity times height. And what I'm saying is that gravitational potential energy gets converted into kinetic energy as the particle is dropping, right? So solving this equation here, because VA is 0, you're going to get your VB. Now notice that the mass is going to cancel as well. So VB is going to be equal to 2 times G times H. I'm pretty sure that you've seen this equation from PSE 1. So that's how you calculate the speed at point B. Now let's look at electric and see what we're going to do here. When I take electric force, electric field, and I multiply that by charge, what is Q times E? It's force, right? Force times distance gives me energy, and all of this energy is the electric potential energy, which gets converted into kinetic energy. So solving this equation, you get VB is equals to 2QE times distance divided by mass. So the reason why I'm showing this example is just I want you guys to see that the two quantities are kind of like. So one problem here is about talking about the force of gravity. And then the second example is just looking at electric. So so when I write this equation here, I want you to understand this equation by saying that, so loss in potential energy is equals to gain in kinetic energy. Because when you take an object, you release it from some height, as the height is reducing, the potential energy is reducing as well. So the change in potential energy gets converted into kinetic energy. All right, let's go back to the PowerPoint. So let me go back to PowerPoint here. I think we have about 5 more minutes. Now, so now we're going to look at what happens when the electric field is not constant. So electric field is not constant. For example, the electric field from the point charge, said that this is not constant. Now, in this case here, I need to use an integral to get the potential difference. And I think because of time here, I think we've already seen this in the previous class here. I'm not going to go over this again because we said that the potential at point A minus the potential at point B is given by this equation like this. And so we can just write down one equation for the potential. It's given by this equation.